Hello, this is the Chapter 11 final video to finish up the Chapter 11 lecture for Chemistry 101, Spring 2021. We left off with talking about polymerization. We said that each monomeric unit is condensed with another or is reacted with another. These chains can link together to give us a wide variety of polymers. Again, PVC, polyvinyl chloride, the white plastic tubing that takes fresh water into and wastewater products out of our house. The polyisobutylene, the skins for many kinds of sports athletic balls, basketballs, soccer balls, volleyballs, and such. And then polystyrene, your foam containers for your eggs, for your food services, for your drinks. Polystyrene is styrofoam, or it is a polymer. Next, we'd like to shift into a six-membered ring known as benzene. These are aromatic compounds. Generally, aromatic compounds are defined by the presence of a six-membered ring with alternating single and double bonds around the entire cyclic ring system. Here we have an expanded benzene ring structure. Every element is represented. Every bond is directly represented by a bond between the two atoms. Immediately to the right, we have a skeletal version of benzene. Each carbon here in the structure is implied as where lines meet, there's a carbon. So lines meet carbon, lines meet carbon, line meets carbon, lines meet carbon, lines meet carbon, lines meet carbon. Again, we assume that there are hydrogens because there's nothing else shown there. Since carbon forms four bonds, we assume that you understand that there's a hydrogen there. There is some unique structural designs present in the benzene molecule. Every carbon and hydrogen in this ring system lies in a single plane. We can draw one plane that contains all the atoms of benzene, so it's a planar molecule. Each carbon is trigonal planar in its molecular geometry about each of the carbons in benzene. So the bond angles between this carbon and that hydrogen are 120. Bond angle between that hydrogen and that carbon is 120. Bond angle between this carbon and that carbon, 120 degrees. So each carbon atom is trigonal planar. So each carbon is trigonal planar, i.e. 120 degrees bond angle, making benzene a planar molecule. This gives benzene some very unique reactive properties that we talk in greater detail about in organic chemistry. We can represent the alternating double and single bonds in an aromatic rings in two ways. We can say that there's a double bond here, a single bond here, double, single, double, single. Or we can draw the aromatic system like this. Where there was a single bond, there's a double bond. Where the double bond is a single bond, single bond, double bond, double bond, single bond, double, double, single. Both of these structures are equally acceptable. Each of these structures has the same arrangements of atoms, but different locations of electrons. These two structures are equally acceptable. These are known as resonance structures. Each carbon is bonded to four things. Each carbon obeys the octet law. But in this structure, we have, starting from here as our reference point, single, double, single, double, single, double. Starting in this compound from its reference point, double, single, double, single, double, single. Each bond in benzene is identical. So it's not this structure nor that structure, but really something that is in between the two. So neither this guy nor this guy are the real structure of benzene, but it's really something that's really a mixture of the two. The actual structure is a combination of both resonance structures, and it's called a hybrid. So this hybrid structure has all three electron pairs, and the double bonds are delocalized in the six-membered ring. So they're not isolated double bond here, isolated double bond here, isolated double bond here, or isolated double bond here, here, and here. They're really a superposition of this upon that. That is why sometimes we draw this circle in the middle. We organic chemists are lazy. If we don't have to do absolutely everything, if we can just slap a circle in there, we'll do it. This is an accurate resonance structure. So is this and this. But this is a better representation because this implies that we have isolated single double bonds. This structure implies that we have isolated single and double bonds. But that's not really what the molecule looks like. It looks more like this, where we have no single, no double bonds. Each bond is about a bond and a half. So this carbon is a bond and a half there, a bond and a half there, bond and a half is 3, 1.5 between here, 1.5 between there. That carbon is 1.5, there to there is that carbon, 1.5, 1.5 and 1.5 is 3, plus the hydrogen is 4. Excuse me. This delocalization, when we represent these double bonds not being either here or here, but all around the ring, this delocalization gives benzene added stability to compared to other compounds that do not have these double bonds. When we talk about naming benzene compounds, if we have monosubstituted aromatic rings, only have one thing on there, we name the substituent first, and then we put the word benzene at the end. So here we have 6 carbons. This is a benzene. We have 2 carbons here. This 2-carbon fragment is a piece of spinach hanging off the aromatic ring. So a 2-carbon fragment is an eth. Since this is a piece of spinach, it's ethyl. So we name this ethyl benzene. Here we have a 4-membered carbon ring. 4 carbons as a piece of spinach is a bute. Since this is a substituent hanging off the ring, it's a butyl group. So it is a butyl benzene. Here we have a Cl. It's a chlorine. So the prefix here is chloro. Since this chlorine is attached to a benzene, it is chlorobenzene. If this was a bromine, it would be bromobenzene. If this was an iodine, it would be iodobenzene. If this is a fluorine, it would be fluorobenzene. So if there's only one substituent, whatever this is named via its regular name, and then it's put on in front of the word benzene. Some of these monosubstituted benzenes have been known since antiquity, and unfortunately some of the names that they had in antiquity have been drugged down to this point in time, such that even when they're listed in precise naming systems, these names that have existed in antiquity still are listed and accepted. So this guy with a CH3 attached to the aromatic ring, this is given the name toluene. The aromatic ring where we have just an OH group, that's called phenol. The aromatic ring with an NH2 group on there is called aniline. So some of these things are named as toluene, phenol, or aniline. Others, notice it's not methylbenzene, it's toluene. Technically, the correct name is single carbon fragment meth. It's a fragment methyl benzene. This technically should be hydroxy benzene. This should be aminobenzene, but it has these names that were given to them in antiquity, and those names have just been brought down through time with no real sense of why this is toluene, why this is phenol, why that's aniline. That's just their names. When you have 2 substituents on an aromatic ring, they can be within 3 relative positions to one another. We can start here, where these pieces of spinach here, these ethyl groups, they are 1, 2. One of these is at the 1 position, the other's at the 2 position. We describe these as ortho, meaning next to one another, or just O, or 1, 2. We describe the position of these two CH2, CH3 groups as meta, 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 or M. The relationship between these three, this one is at 1, that one is at 3. Or if you choose, this one is at 1, 2, 3, and that one is at 3. So meta, or M, or 1, 3 dash diethylbenzene. A 1,4 substituted aromatic ring is a para. So this is para diethylbenzene, or P diethylbenzene, or 1,4 diethylbenzene. So just depending upon where these two groups are with respect to one another around the ring, if they're immediately next to one another, they are ortho, 1, 2, or O. If they are 1, 3, they're meta, or M. If they're 1, 4 in relationship to one another, that is para, or P. When we have two groups that are not alike, we list them, and the first substituent that comes alphabetically is the first position. Bromo is at the 1 position, but the bromo and the chlorine are next to one another. So the bromine's at 1, the chlorine is at 2. So we can say O-bromochlorobenzene. The O relates the position of the bromine to the chlorine on the aromatic ring. They are 1, 2 next to each other, so O-bromochlorobenzene. We could say 1-bromo-2-chlorobenzene. Or we could say orthobromochlorobenzene. These three, this ethyl group and this fluoro group, which comes first, E or F? Alphabetically, E comes first. Therefore, since the E refers to this is position 1. So this is 1, 2, 3. These are 1, 3. These are meta to one another. So it's meta, or M. Ethyl comes first, fluorobenzene. So when you have two substituents, you alphabetize them. The first one listed is the number 1 position. Unfortunately, if you have two substituents, and one of the substituents is one of those compounds from antiquity, you name it as a substituted compound based on the name in antiquity. So if we just have this guy right here, no bromo here, this is toluene. But since we have the bromine, there's a disubstituent. We say P-bromotoluene. Toluene has the CH3 at the 1 position. So toluene names this. But now you have this substituent, and you're saying, what is the relationship between the Br and the CH3? It is para, or 1, 2, 3, 4 carbons away. So this is para-bromotoluene. Here we have the derivative phenol. So this is a substituted phenol. What is it substituted with? A chloro group. But where is the chloro with respect to the OH? The OH is 1. This chlorine is at the 2 position. So it's a 1-2 relationship, or an orthochlorophenol. When we have multiple substituents, more than 2 around the aromatic ring, you number to give the lowest priority to the groups around the ring. You alphabetize the substituent names. If a substituents are part of common roots, you name the molecule of that derivative of that monosubstituted benzene. The predominant group is at C1, but many times you can omit the 1 from the name. Here we have this 6-membered ring. We have a ethyl group here, we have a propyl group here, and a chloro group there. None of these have an existing name that comes from antiquity. Therefore, we number around the circle such that the numbering sequence gives us the lowest number possible. So let's say if we start with 1 here, we go 1, 2, 3, 4. That's a 1, 3, 4. If we start with 1 here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. But if we start with 1 here and we count 1, 2, 4 clockwise, with this being at 1, gives us the lowest numbering sequence around the ring possible. So this puts the ethyl group at 1, this 3-membered propyl group, C3, at 2, and the chloro at 4. But we list them alphabetically. Numerically, their numerical position is determined by what position we label as 1 and how we label around that ring such that the numbering sequence is as low as possible. So in this, 4 chloro, 1 ethyl, 2 propyl, benzene. We have a chloro group at 4. At the 1 position, we have an ethyl group, a 2-carbon fragment. At the 2 position, immediately next to the 1, we have a 3-carbon, a propyl substituent. All of these are put onto a benzene ring. Here, we have a substituent on the aromatic ring that it's a compound that has been named from antiquity. This particular example, the NH2 group attached to the aromatic ring, is an aniline. So we're naming this compound as a substituted derivative of aniline. So aniline takes care of everything that's in brown. Therefore, if we're saying it's an aniline where the nitrogen is attached to the ring, that's the C1. Now we need to determine, how do we number around the ring? Do we go counterclockwise this way, 1, 2, 3, 4, 5, or do we go clockwise around this way? Well, what gives us numbering here is 1. What gives us the lowest numbering possible? If we go clockwise, it's a 1, 3, 1, 2, 3, 4, 5, 6. It's a 1, 3, 6. Going around this way, it's a 1, 2, 3, 4, 5, 1, 2, 5. So the lowest numbering sequence is we go 1, 2. It puts this second substituent at the number 2. This gives us the lowest numbering sequence possible, therefore we number counterclockwise. This is 2, 5, 2, where the nitrogen is attached to the ring, that's the 1, 2, 3, 4, 5, 2, 5 dichloro, aniline. There are a number of aromatic compounds that contain more than one aromatic ring attached to another. Very common, naphthalene, mothballs. This is anthracene, 3 aromatic rings fused together. You can have rings that are sitting not in a line, but either up or down off of a conjugated sequence. So this is known as phenanthrene. Again, there's any number of these organic compounds where we can have the ring here, or here, or here, or here, or here, and it has a different name. But there are a number of these aromatic compounds that have more than one aromatic ring attached to it. That's chapter 11. Hopefully this has been an interesting review for you, and I will see you in class. Have a good evening.